Welcome back, everybody. So what we're going to do here in the next couple of sections of the text is prove a couple of interesting identities. I probably am just going to do both of these sections together rather than try to break them apart. What I want to do is I want to first prove really there's 6 identities, but 3 classes of identities. So without further ado, I'm going to shift over to my document camera here real quickly. And okay, so this is the way that the textbook does it is we prove the fundamental identity related to the sum and difference for cosine. So sum and difference of 2 angles. I believe that's the way the textbook does it. I'm not really pleased with the way my document camera is showing. Okay, so let me start by drawing. Let me just make some comment here. So currently, we have not done anything very interesting with the arguments of individual trig functions. But what we would like to do is we'd like to be able to say, okay, if I have a trig function of a sum of 2 angles, I'd like this to be some kind of function of trig functions of A and B. And here's the rationale for this. For example, I know what the cosine of 45 degrees is. I know what the sine of 30 degrees is. I know the sine that these are known quantities. But what I don't know is maybe something like this. What's the cosine of 75 degrees? Well, what I would like to do is be able to come up with a formula that relates this to known values. So we're in some sense we're expanding the number of exact values that we're aware of, right? So this might have something to do with sine of 30. Maybe it has cosine of 45 in there. Some kind of relationship that puts all those together. So I'm going to try to be really careful about drawing this picture for you. I'm going to prove the relationship for cosine of A plus B here, and then we're going to extrapolate that to other versions. So let's start by drawing a coordinate axis. Okay. And I'm going to prove this where A plus B is in quadrant 1. It's easy enough to show in other quadrants, but you have to do some interesting things, like you have to reflect some stuff and move things around, but it all works the same. So we'll start by proving things in quadrant 1, and then we'll show that this expands to different formulas for sine and tangent and everything else. Okay, so what I'm going to do is I'm going to shift to a different pen because this is going to get messy in here. So the first thing I'm going to do is I'm going to draw in maybe what we would call angle. Let me do it with some Greek letters so we're real clear what's what. So let's say that this is angle alpha. All right. And this is angle beta. Okay. So the angle that I've drawn from the x-axis to this terminal ray is actually the angle alpha plus beta, right? So this one, the measure of this angle is alpha, the measure of this angle is beta. The sum of them, you've got this whole thing. Okay. Now, what I'm going to do is I'm going to start drawing a couple of extra lines here. So just at some point, I'm going to label this down here as point O for the origin. And then I'm probably going to pick a point up here like we've done often. I'll call that point P. And then I'm going to draw a perpendicular line from P to the x-axis, okay? And where that crosses at several different places, I'm going to, let's see, so P, Q, R, right? And then I'm going to draw from point P a perpendicular to this terminal ray as well, okay? And I'll call that, let's see, that's QR, this will be point S. From this point, point S, I'm going to draw perpendicular down to the x-axis. I'll call that point T. And then finally, I'm trying to remember how many other points I need. I'm going to draw from point S perpendicular to the line segment PQ. Okay, and I'll call that point U. Now, the first thing I'm going to do, and this may seem a little bit strange, but I'm going to try to find that angle up there, angle UPS, right? Because it's going to allow me to make a couple interesting arguments. So first, notice that angle alpha is part of this right triangle OQR. So I'll just kind of put over here to the side. Observe, triangle OQR is right. Okay, so since that's a right angle, since that's a right triangle, that means that this angle up here, ORQ, is actually the complement of alpha. So I'll make that argument too. So angle ORQ is equal to 90 degrees minus alpha. Okay? So far, so good. So this is the complement of alpha. And that means that angle PRS, because it's a vertical angle, must be equal. So angle PR, let me just start, I got a messy here. Okay, so angle PRS equals angle ORQ. Okay, and I could say because vertical angles or something along that line. Right? Now, that tells you that this angle here is the complement of alpha as well. So complement of alpha, complement of alpha. Now notice that triangle RPS is also a right triangle. So observe triangle RPS is right. Okay. And therefore, whatever this angle is, angle RPS is the complement of it, right? So we have alpha, complement of alpha, complement of alpha, complement of the complement of alpha, which is the same thing as alpha, okay? So the net result is that angle RPS is equal to alpha, okay? That's sort of a geometry conclusion, all right? And I'm going to go ahead and label that in our diagram here now that we know it, okay? Now I'm going to move to another page here at this point, but at this point it'll become very much a bunch of just line segments. I may refer back to this drawing. I'll pull it back in as needed. Section 5.3, page 2. Okay, so I'm just going to kind of have this here. So Now what hopefully everybody can see is that, now remember, we're looking at cosine. So if you're looking at the cosine of alpha plus beta, notice that that can be described by different line segments from triangle OPQ, right? Here's this right triangle, and this angle down here is alpha plus beta. So the cosine must be the adjacent over the hypotenuse, okay? So moving back to my other sheet here, I'm going to say, note, cosine of the sum, alpha plus beta, is equal to line segment, and I'm going to lose the line over the top of them. I think it's understood. It starts to become messy because of the thick tip on my pen, but it's the adjacent over hypotenuse, which in this case is OQ divided by OP. Okay, and I'll just drop this picture back. So cosine of this sum angle is the adjacent over the hypotenuse, OQ over OP. Okay, so that's kind of a start. Now, what I'm going to do is I'm going to start doing some manipulations here, where I start to break this into a couple of different pieces, and I institute a value, a quantity over a quantity, and I do some sort of algebraic trickery here. But here's sort of the play-by-play. So the first thing I do is I say, well, notice that this length down here, OT, is actually OQ plus QT. Now what I'm going to want to do is I'm going to want to write OQ as OT minus QT. Okay, so that's sort of the first step. So I'm saying this is the numerator of this expression becomes OT minus QT all over OP. Okay, does that make sense? Hopefully. I don't get much feedback from these videos. So now I'm going to split that into two different fractions, OT over OP minus QT over OP. Okay, so the next step is that I'm going to institute a ratio here that it's kind of going to look a little strange what I'm doing, but it's kind of an old school trick that you know, the only thing that mathematicians are ever doing is they're multiplying things by 1 or they're adding 0 to stuff. It's just that those look a little strange. So what I'm going to do with this first term is that I'm going to multiply it by the length OS over OS, and OS is this length right here. It happens to be the hypotenuse of the right triangle with angle alpha as one of its acute angles. Okay, that's sort of the rationale for it. For the second term, I'm going to multiply by PS. So I've got QT over OP times PS. And notice PS is it's not the hypotenuse, but it's one of the legs of this right triangle. It also, what's interesting is that PS is one of the legs of well, it's the hypotenuse of a right triangle that has an acute angle of alpha, but it also happens to be the opposite of a right triangle that involves beta, and that's really the key there. Okay, so at this point, again, I'm going to do a little bit of algebraic trickery. What I'm going to do is I'm going to exchange. I'm going to exchange the denominator here. So I end up with OT over OS times OS over OP. And then with this term here, I'm going to do let me just make sure I'm doing this right. Oh, QT. Yeah, I'm gonna exchange these right here. So QT over PS times PS over OP. Okay, just a little bit of flip-floppery. Now, the other thing that I want to point out, I've got to be careful here. That's QT. If you look back at the diagram, notice that QT, well, actually, there's this quadrilateral USTQ. It's a rectangle, right? And so one of the results is that QT is actually equal to US, right? QT equal to US. So I'm going to make that substitution here. I'm going to transform that into US. So I have OT over OS times OS over OP minus US over PS times PS over OP. Okay, and I think I got those in the right order at this point. So let's take these term by term, okay? Because basically these are now trig functions because they're ratios of legs to hypotenuse. So let's look at OT over OS. Here's OT and here's OS. Notice OS is the hypotenuse of a right triangle whose acute angle is alpha, and OT is the adjacent side. So OT over OS is equal to the cosine of alpha. So I'll go ahead and write that in. So this is cosine of alpha, okay? Let's look at OS over OP. So back to the diagram, here's OS, and here's OP. Notice OS is this triangle OPS is a right triangle whose acute angle is beta. And the adjacent side is OS, and the hypotenuse is OP. Well, that's the ratio of those two is actually the cosine of beta, right? So OS over OP is equal to cosine of beta. Okay, so what about these other two terms? Well, the one that we're looking at here is US over PS. Let's find US, PS. So here's US and here's PS. Notice that for this triangle UPS, that's a right triangle, and PS is the hypotenuse and US is the side opposite the angle alpha. Okay, so this is opposite over hypotenuse, and that happens to be the sine of alpha. Okay, finally, let's look at PS over OP. So let's find it on the diagram. Here's PS and OP. Notice again, here's this right triangle. PS is the side opposite beta, and OP is the hypotenuse. So we have opposite over hypotenuse, angle beta. This is sine of beta. Okay, so there's box it, bullet it, whatever. This right here is the formulation for the cosine of a sum. So what's the point here? Well, if you know the cosine of alpha, cosine of beta, sine of alpha, and sine of beta, you can now find what the cosine of the sum is. All right, and I think what I'm probably going to do is I'm going to probably derive the rest of the results, and then we'll actually look at some applications. So this is basically the formula for cosine alpha plus beta, and I will come back on the next one and show you cosine a alpha minus beta, sine of alpha plus beta, sine of alpha minus beta, tangent of alpha plus beta, tangent of alpha minus beta. So stick around.